Hello, I'm Ehsan Tousi, a graduate student at Western University in Canada. The title of my poster is Unsupervised Object Learning Explains Face but Not Animate Category Structure in Human Visual Cortex. So prior works show that high-level visual human cortex represents natural categories of ecological relevance, including faces and animate objects. Deep neural networks, which are currently the best computational models of the primate visual system, tend to show a weaker natural category structure in their internal representation. And the difference between humans and neural networks may be driven by differences in learning objectives, which reflect the computational goals of the system. Humans learn to understand the world through both supervised and unsupervised learning. When a child sees an object and his father says that the object is called a dog, the child is subjected to supervised learning. The learning goal here is to map visual input to category labels. However, children learn about the world before they understand language. Furthermore, their parents only provide labels occasionally. So children may also learn by attending to similarities between objects and discover natural groupings corresponding to categories. The learning goal here is to discover a structure in the data. Hence, unsupervised learning does not require labels. Deep neural networks are standardly trained using supervised learning only, which may contribute to differences in object representations between humans and neural networks. Here, we test what information unsupervised learning can extract from natural images and whether this information matches the information extracted by humans. Therefore, we hypothesize that unsupervised learning will yield brain-like object representations that emphasize natural categories. For supervised training, we have a label for each image, like we have the label dog for this image. During training, we adjust the network's weights such that it gives the same output as the target label. For unsupervised training, we use the recently developed contrastive learning algorithm. We create two views for each image and train the network's weight such that two views of the same image evoke the same representation or attract each other, and views from different images evoke different representation or repel each other. As I mentioned, unsupervised learning does not require labels. This removes the reliance on experimenter-defined category labels, which is prominent in supervised learning. To test our hypothesis, we train ResNet-50, a deep feed-forward convolutional neural network on ImageNet, using both supervised and unsupervised learning algorithms. Then, using representational similarity analysis, we compared the object representations learned by the networks to object representations in human IT, which were measured with fMRI. We focus our analysis on the last convolutional layer of the ResNet-50, which is positioned at a location in the processing hierarchy similar to IT cortex. Now I'll show you RDM movies which show how the representation of the objects changes during supervised and unsupervised training. We can interpret these movies as learning trajectories. On the upper part, you see snapshots of the movies. The appearance of the snapshots is synced with the movies. We can see that learning trajectories differ between supervised and unsupervised training. Visual inspection of the network's representations suggests that unsupervised learning yields a clear cluster of faces, which we can also identify in the human IT data. However, neither of the networks show a clear clustering of animate and inanimate objects. To quantify these observations, we first correlated the network's object representations with the human IT object representation and compared model performance using bootstrap resampling of the image set. The unsupervised network better explains the human IT object representation than the supervised network. This difference emerges relatively early and increases as learning progresses. Performance of the unsupervised model reaches the lower bound of the noise ceiling, which indicates performance of the unknown tool model given the noise in the fMRI data. Before moving on, I want to highlight 2 points here. First, without using labels, the unsupervised model learns a representational structure similar to human IT. Second, the unsupervised model may be superior because it is not constrained by the ImageNet labels during training. ImageNet labels, which are used for supervised training, do not fully overlap with natural categories of ecological relevance. To better understand why the unsupervised network better explains the brain data, we examined the relative contribution of different categories to human IT and the network's RDMs. To do so, we fit a category model to all RDMs using linear regression. We plotted the estimated weights for category predictors that were significantly different from 0 for human IT. In all plots, the y-axis denotes the predictor's weight and the x-axis shows training epoch. The gray line shows the weight for human IT, the dark purple for the unsupervised network, and light purple for the supervised network. Shaded regions reflect a standard error based on bootstrap resampling. Asterisks indicate significant differences between supervised and unsupervised models and humans. Our results indicate that clustering of animate and inanimate objects is weaker in both networks than in human IT. However, for face clustering, the unsupervised network is not significantly different from human IT. To conclude, unsupervised learning yields brain-like object representations that emphasize natural face category structure. Both supervised and unsupervised models fall short of predicting the category division between animate and inanimate objects in the human brain data. These findings suggest that it's challenging to learn this category division from static images alone. Our findings highlight the potential of unsupervised learning for improving neural networks as models of the brain. Thank you all for watching.